Hi, welcome to the Unit 2.1b Solutions Chemistry video notes. These video notes are broken down into 3 parts. This is part 1 of 3. Be sure to annotate as always, and there are some optional videos embedded here. In this video, we're going to continue on our discussion of describing what happens during dissolution. During the 2.1a video notes, we had the following success criteria. So I introduce you to the term dissolution, ionization, electrolyte, non-electrolyte. We also learned how to recognize different types of electrolytes, salts, acids, and bases from their chemical formula. We also defined acids and bases using Arrhenius and Bronsted-Lowry definition. We really focused on the Arrhenius, but we did use the Bronsted-Lowry to define amines since they didn't fit under the Arrhenius definition. And then finally, we showed what happens both in words and in chemical equations when we dissolve a salt, acid, and base. We're going to continue utilizing that knowledge here. So let's just quickly recap. When we say electrolytes, that means that's something that ionizes or breaks apart or disassociates into its ions in water. And non-electrolytes, they break into smaller pieces but do not disassociate. So that means that not all dissolutions, dissolution means to dissolve, are equal. So if you take something like sugar, if you dissolve it in water, what will happen is the sugar molecules, which are all kind of like clumped together, will start to, separate, right? But they'll still say one whole molecule. Whereas something like sodium chloride, it's going to break apart into its cation and anion. And it's allowed to do that because the water is polar and it's sort of the oxygen part of the water will surround the cation to stabilize it, and the hydrogen part of the water will surround the anion to stabilize that. So that happens with something with sodium chloride. But is that true for all salts? Let's take a look at something like silver chloride. You'll notice here that there is a different type of arrow notation. It's a double arrow. Why do we have that? Let's take a look at what happens when we dissolve silver chloride in water versus sodium chloride. So here's sodium chloride on the left. You dissolve in water and it pretty much looks like it's a homogeneous solution. So that's telling you that it's all sort of like one thing according to our eye or under the microscope. So everything was blended nicely. All of it, or almost, or virtually all of the sodium chloride was able to break apart into its ions. Well, on the right hand side we have silver chloride. That doesn't look so nice, does it, right? So what do we have with what's going on with silver chloride? Well, some of it is dissolving, but most of it it's not. And we have sort of this process here where some of it dissolves, but then a lot of the stuff that did dissolve, it's going to recombine to form this silver chloride. This will become more clear when we talk about equilibrium, but at any rate, we use these double arrows to sort of show that not all of this is going to break apart into its ions. Okay, so it does not completely ionize. All right, so how can you tell what's going on with ionization? The ionization of salts depends on the solubility, and in order to know whether or not we're using single arrows to show it's going to completion or double arrows to show that it's incomplete, we have to know the solubility of the salt or the ionic compound. All right, so soluble again means to dissolve in water, and insoluble means it does not dissolve. And so we have an example here of magnesium sulfate, which is Epsom salt. That dissolves pretty well in water, and people use it in their baths all the time. Where something has milk of magnesia, which is used to treat like stomach ailments, it's also a magnesium salt, so magnesium hydroxide. That is insoluble, and you can see, like, if you look at it, it does not look like like water. It's sort of this milky, gooky solution. All right, and we have a range of solubility for hydroxide. So here at the top, we have the ones that are soluble, somewhat soluble in the middle, and then towards the end, we have insoluble. So the question is, well, how can you tell if something is soluble or insoluble by looking at the chemical formula? For that, you have to use the solubility rules. And these are listed in order of priority, meaning that the first rule is the most important, second rule is second in importance, etc. So that means that if, in order to fulfill the fourth rule, you have to violate the first, you wouldn't be able to do that. However, you could violate the fourth rule to satisfy the first. All right, so what are the rules? The first rule is that all nitrates and acetates are soluble, meaning any salts with nitrates or acetates in it will dissolve. Second rule, most group 1 metals, and the only exception is francium, are soluble, and ammonium, and you'll have to change that in your handout, by the way, sorry about that. That should be ammonium, I-U-M at the end there. NH4 pluses are soluble. So if you see a group 1 metal or NH4 plus in the ionic compound, you should assume it's soluble. Next rule, most chlorides, bromides, and iodides are soluble with the exception of silver. So we just saw silver chloride, that's not soluble. Lead 2, and this dimercury here. These are insoluble. So any of these type of halides, chlorides, bromides, iodides, they will be insoluble. The next rule, most sulfates are soluble with the exception of barium sulfate, lead 2 sulfate, dimercury sulfate, and calcium sulfate. Okay, so now we're going to go into rules about things that are insoluble. So now we're sort of like flipping the switch. That's why I changed the color. So these rules are now talking about things that are mostly insoluble with some exceptions. So most hydroxides are insoluble or only slightly soluble, and the exceptions for that, barium hydroxides, strontium, and calcium hydroxides, these are all soluble. So these things are soluble. All other ones, of course, unless they're group 1 metals and etc., are insoluble. Remember that we cannot violate, like let's say we can't violate rule 2 to fulfill rule 5. So rule 2 is more important than rule 5. That's why group 1 hydroxides are soluble. And that's when most sulfides, carbonates, chromates, and phosphates are insoluble. All right, so you have to memorize these rules, and you can memorize them by making flashcards, doing a bunch of practice problems, but I also embedded some optional videos that could help you with your solubility rules. Some of them are songs and and a mnemonic device. You can choose if you would like to use them, but they may be helpful in memorizing solubility rules. All right, once you have those memorized, or you refer back, you're going to try this TFU. There are several parts here, so pause the video now, read through, and when you press play again, the answers will be revealed. All right, so here are the answers to the CFU. First one is false. Group 1 metals, not all group 1 metals are soluble. Most are. The only exception is francium. True, all nitrates are soluble. False. Not all chlorides are insoluble. In fact, most chlorides are soluble, meaning that most chlorides will dissolve in water, the exception being the lead, the mercury, and then the silver. Barium hydroxide is soluble, so it's one of the exceptions to the insoluble hydroxide rules. And then if we're labeling this, magnesium nitrate is soluble because it has a nitrate. Remember, all nitrates are soluble. And this is insoluble because although most chlorides are soluble, the ones with lead 2 in it, for example, are insoluble. Okay, what about ionizations of acids and bases? So if for salts it depends on solubility, for acids and bases it depends on their strength. And we're going to talk about that. So just to recap, acids, when they ionize, they form H+. And if you have something like a strong acid, I put the acidic proton here in the front, and this is the anion. Again, we use this single arrow because it all dissociates, all dissolves. All right, and then here are the list of strong acids, which you will have to memorize these. So take a moment to look at these. We'll talk about naming rules later, but this is hydrochloric acid, hydroiodic acid, hydrobromic acid. This is chloric acid, nitric acid, and sulfuric acid. Any other acid that's not on this list is considered a weak acid, and when you dissolve those in water, you'll have to use these double arrows because they're showing you that not all of it will ionize. So again, you have to memorize these. You can make flashcards or maybe Google to see if there are any videos to help you memorize which ones are strong acids or not, but you definitely need to memorize strong acids. And if it's not a strong acid, then you consider it's a weak acid. All right, bases, sort of the same thing. So again, bases ionize into hydroxides, and we'll look at amines later. But the group 1 hydroxides, except for francium, of course, and then these 3 group 2 hydroxides are strong. They pretty much follow the solubility rules. So any hydroxide that's soluble, meaning it dissolves in water, is a strong base. On the other hand, for a weak bases, anything else that's not on this list will be considered weak, and we use these double arrows. Amines are also considered weak bases, so just all amines are weak bases. All right, so now it's time to try this CFU. It's the same sort of thing. Pause the video, and when you're done, the answer will be revealed. All right, so here are the answers. Is there anything that you're not sure about? You want to definitely come in with questions. So what we're going to do now is we're going to move on to part 2. So this video will stop, and then you'll go on to part 2. Have a quality day.